Math 242, Quest to College. I'm Joe Vasta, and we're going to cover section 11.10, Parametric Equations. The homework is completely a handout, which is on the main part of my webpage, but I'll also include it with the PDFs right next to the video. The other caveat is if you have the printed book, 11.10 is not in it. So you might say, well, how do I get that? You can go get the PDF that's on my website, and it includes 11.10. But I'm not assigning any problems from that because it's mixed with trigonometry. And reading 11.10 actually might be more confusing than just looking at this lecture. So, to get things straight, the homework is a handout that I made, and it doesn't have any trigonometry in it. So, parametric equations. We have parametric equations right here. And what is this? This is sometimes called a system of parametric equations. And T is called the parameter. Okay, let's go ahead and see if we can graph these parametric equations. Oh good, I found what I was looking for here. And we're going to need the help of this bug to do this problem. And it's looking pretty clear, so let's go ahead and figure this out. So T is called the parameter, sometimes it's called time. And this is going to be kind of weird, the first one we do. I'm going to go ahead and go like this. And remember, we used to plot points on graphs, and we would go X and Y. Now it's going to be a little bit more complicated. I'm going to say time, T, and then I have X, and then I have Y. So I'm going to go ahead and plot T equals -1. Is there a negative time? Yes. 1 minute ago was -1. And then we have 0, 1, 2, 3. Just plotting a few times. And what I do is I'm going to plot each of those values. There's 5 t values. I'm going to put them into the x equation. So when time is -1, we end up getting -2 minus 2, which is -4. Time is 0 in that x equation. We have -2. Time is 1. We have 0. You might even see a pattern here. Time is 2. We have 2. Time is 3. We have 4. So it's a linear pattern. And that is a linear equation, so is y. So now I'm going to let t equal -1 and all those values in the y equation. So t is -1, I end up getting 12. T is 0, we have 8. T is 1, I have 4. T is 2, I end up having 0. And t is 3, we have -4. Okay, so what is this? What is this? What have we just done? Well, this right here, this -4, comma 12, that is a point. -4, comma 12. And the next one is -2, 8, and 0, 4, 2, 0, and 4, -4. So those are 5 points that I can plot. I might not plot that point up there because we'll have to see how we do here with this. So here are some axes. What are the instructions? Well, there are no instructions. We're just kind of seeing what parametric equations are. And so we're just kind of exploring this. So I have the point 0, 4. 1, 2, 3, 4, so we have that point right there, and maybe it would be better if I had grid paper. -2, 8. 1, 2, 3, 4, so here's 8. It looks like that right there. And then we have 2, 0. Okay, so there's 2, 0, and then 4, -4. Just like right here. Okay, so those 4 points, and I could have put the fifth one, the -4, 12 is like up here. They all lie on the same line. And if I was using grid paper, it would be even more precise. And so the line looks like that. Now, I'm not going to put arrows on both sides of the line, okay, because there's a reason for that. And so I have just graphed this system of parametric equations, and it is a line. Now, here's the other thing with this line is this tells us, the parametric equations tells us there's a bug crawling on this graph. And so there's the bug, and at time 0, he is at -2, 8. So this is time equals 0, he's there. And at time equals 1, he's right here at 0, 4. See, time equals 1, he's at 0, 4. So I'll put time equals 1. And at time equals 2, he's at 2, 0. And at time equals 3, he's at 4, -4. 1 second ago, at time equals -1, I think he was up here at -4, 12. And so what is the bug doing? He's walking this way on the graph. He's going like that. Well, so when you have a system of parametric equations, this curve that is described by this system has something called an orientation. So the orientation is which direction the bug is moving. So there is an orientation on the curve. And all it means is which way the bug is walking. So he's walking down. So think of these parametric equations as a bug crawling on a curve. This is used in calculus. And a question that may be asked here is, what is the equation of the curve, or of, in this case, of the line? So that is our question. What is the equation of this line? Well, probably a simple way to do this is to look at this. Y equals mx plus b. We know that the y-intercept is at 0, 4. The y-intercept is 4. And we could probably see the slope. If we do rise over run, we rise up 4, we run over -2, so that's 4 over -2, so that's going to be -2 is the slope. So the equation of that line is this right here. Now here's the problem with this. There's nothing wrong with this. That's the equation of the line. But when you have this as opposed to this system of parametric equations, this does not have the orientation. In fact, we lose the orientation on the curve when we switch it to the rectangular equation. Sometimes this is called the rectangular equations. So that is what you're going to be doing in your homework. They're going to be giving you some parametric equations. They're going to ask you to graph, including the orientation, and then they're going to ask you to find the rectangular equation of the curve. Before I go ahead and do problem 2, I'm going to show you another way of finding this equation of this line. Okay, and some of you might not like this. I'm going to go ahead. I'm going to get the same result. And this might be needed if the problems are a little more complicated. So I'm just rewriting that down. So another way of finding y equals -2x plus 4 without saying what is the slope, what is the intercept, is you solve for t in one of these equations. So I'm going to solve for t in this top equation. I'm going to get x plus 2 equals 2t by adding 2 to both sides. And I'm going to divide everything by 2. And I'll switch it around. So t equals x plus 2 over 2. This might remind you of systems of equations a little. I'm going to plug that into the other equation. I'm going to plug that in for t. So I have y equals -4t, which is x plus 2 over 2 plus 8. Now notice what happens here. This 4 and this 2 cancel. This gives me a 1, and I still have the negative there, -2. So this gives me -2 x plus 2 plus 8. And what does this give me? This gives me y equals negative 2x minus 4 plus 8. And so y equals negative 2x plus 4 is the rectangular equation for those parametric equations there. And look what we have here. This matches the one that we got when we just looked at the line. So when you're doing your homework, you know, you can use either method to find that. And that completes this problem here. And we didn't even really ask you or give you instructions on this. So I'll give the instructions that would also count for the problem that we just did. So that's parametric equations. Why do we like them? We will see. We'll see some crazy examples as well. So here are the examples. Find a rectangular equation of the curve. We actually did that second, and that's alright if we do that second, and then graph, including orientation. So some people might actually find the rectangular equation of the curve by solving for t and plugging it into the other equation or whatever that, you know, and then graphing it, but you still have to include the orientation. So I'm going to just do this the regular way. Now, another thing that comes to mind is this looks like the last problem we just did. Here's the last problem we just did. But there is a difference between problem 1 and problem 2. Maybe you can see that difference. The difference happens to be we're limiting our t's. So t is between 1 and 3. So what I'm going to do, I mean, we did a lot of this before. I'm just going to go like this. I have t here, x there, and y there. And I'm going to put 1 here and 3 there. And so I'm kind of copying what I had here. When I put 1 in for t, I end up getting 0, 4. And when I put 3 in for t, I end up getting 4, negative 4. So t can only be, the times can only be between 1 and 3. I'm going to draw a picture that looks kind of similar, but there is a difference between this and problem number 1. So let's see if we can see the difference. So 0, 4 is right here. 1, 2, 3, 4. I'll put a point there. And for negative 4 is down here. So 1, 2, 3, 4, 1, 2, 3, 4. And I'll put a point down here. Now I know from the last problem that it actually also went through the x-axis at 2. And it looks like that right there. Now notice, okay, besides this thing smearing here, notice, you see kind of the difference? The difference is that this line is not going to be a full line, it's going to be a line segment. It's going to start right up here at t equals 1, and then the end is going to be when t equals 3. The orientation is still going down, and it looks like that, but notice the difference between the graphs. This graph goes forever, and that's a line, and this is a line segment. The rectangular equation will still be the same. Y equals negative 2x plus 4. I'm not going to go through that again. But we have to put a comma and say our x's are going to be between where? Where's the x's? So look at the x's now, not the t's. It's going to be between 0 and 4. So our x's, 0 less than or equal to x, less than or equal to 4. X is sandwiched in between those. So we don't have a graph where x equals 5 or x equals 10 or x equals negative 1. That is what the graph looks like. We still lost our orientation when we wrote down our rectangular equation, but that's just the way it goes. So here is another problem. Yeah, of course, it was like problem number 1. So let's go ahead and do another problem. Something that looks different. So, you know, these guys, look, these problems look the same. 2t minus 2, negative 4t plus 8. Let's go do something that looks a little different. And so our next one is this one right here. It says, x equals negative 1/2 t plus 7, and y equals t minus 10. Okay, so that looks different from the other problem. And my t values are between 6 and 14. And here's another thing to note about these parametric equations. When each of these parametric equations is a line, you know, this one's a line and that one's a line, then your end result is going to be a line. Now, because we are trapped between those two times, ours is not going to be a full line, it's going to be a line segment. So this is what I would do on this problem. I would go ahead, put t, x, y, and because I know it's going to be a line segment, I'm going to go ahead and just put the beginning time of 6 and the end time of 14. I'm going to plug those into them. I'm going to do this a little differently. I'll plug 6 into x and y, and then I'll do the 14. So if you plug 6 in for x, you're going to get 6 times negative 1/2 is negative 3. Negative 3 plus 7 is 4. You plug 6 in for y, you get negative 4. Now I'm going to plug 14 in for these. I have negative 7 plus 7 is 0. And 14 minus 10 is 4. So right now you're probably getting a little freaked out because something is looking very familiar. And I did this on purpose to illustrate a point. Okay. So what we have is we end up having x and y and 0, 4 and 4 negative. Okay, so let's do 4 negative 4. We have a point right there, and then we have 0, 4. So what I'm saying you might be getting freaked out about is this looks like the same problem. Looks like problem number 2 where we had, in fact, look at this. Looks like problem number 2. You had 0, 4, 4, negative 4, but there's something different about this. So this right here is when time was, we got this point when time was 6, and we got this point when time is 14. So what does that tell you about? This is a line segment. It is the very same line segment as the last problem, but what is the orientation on this line segment? The orientation is going up. So now the bug is traveling from here up to there. And even though it gives us, it looks like the same answer, it's not exactly the same answer. In fact, you could say that the bug is traveling faster on this one. From 1 to 3 seconds it goes, but then this one it takes like about 8 seconds to go between the same 2 points but the other way, so it's actually going slower. And it's kind of funny because it's the same line segment but it's different parametric equations. So this just goes to show that the same curve can be parameterized many different ways, in fact infinitely different ways. You can parameterize a line segment or a line or a parabola or any other curve. Now, because we know this is the same line, we can do the same thing. Y equals negative 2x plus 4. X is between 0 and 4. So based on that right there, you know, we looked at that in the last one, so that was the last one. You wouldn't even know they were different. But because we had this, you know, the parametric equation shows you they're different. There's different orientations, and we're not going to be asked this in the homework, but there's different speeds of the bug. So I promise you, problem number 4 will be different. It won't be that same line segment. I wanted to do a different one now, just so you wouldn't think that I'm going to do the same problem each time. So here is problem number 4. There are a few ways of doing these problems. Once again, some of you would find the rectangular equation first and then graph that. I'm going to do what I've been doing. Okay, so now this is different because it says t is greater than or equal to 0. So when I go like this, I have t, x, y. Might as well put the starting point of time 0 there. And I end up getting 1, negative 1. I could put time equals 1 in, and I end up getting, for x, 2, 1. And that's all I need, because this is a line segment. I mean, this is a line, so we know that the parametric equation will be a line. Let's see if we can graph this. So here's x, here's y. I'm going to graph, so you can go like this actually. There's the first point, there's the second point. 1, -1. There's a point right there. And then we have 2, 1, which puts a point right here. And you notice that time starts at 0, and then we have this right here. It's going like this. And I really should be just using the ruler. And then at time 2, it's going to be, 3 something. And so it looks like it's going to go like that, like something like that. Now, it's going to keep going, so it will go right off the page probably, right onto the desk. But it has to actually not go on the other side of this point, and the reason for that is because t is greater than or equal to 0. So it's not a line segment, it is not a line, and from geometry you might remember the word for something that starts at a point and goes off to infinity. That is called a ray. The orientation on this, see, the bug was right here at time 0. The bug was right here at time 1. The orientation is going that way, so we put an arrow there. Now, I've seen teachers put like 5 arrows on this. You can put an arrow here, an arrow there, and it's just indicating the orientation. So that gives us this one. And you can find the slope. I think the slope is 2, and the y-intercept, you can figure that that's going to be -3, and do it that way. I'm going to go ahead and do it the other way, okay? So what am I doing? I'm finding the rectangular equation. So I have the graph, check, rectangular equation. I'm going to solve for t in the first equation. So t equals, what, x minus 1? Then I'm going to plug that into the second equation. So we go like this, and we go like, that's going under there, and then we have what? We have y equals 2 times x minus 1 minus 1. So this y equals 2x minus 2 minus 1, y equals 2x minus 3. Now I think I said that because the slope is 2, and if you kind of keep, you don't want to draw that, but if you kept drawing that, you'd end up hitting the y-axis at -3. Now a lot of people would just put this for the answer, but we have to actually limit our domain. X can only be what? It can only be greater than or equal to 1. So x is greater than or equal to 1. And there's the rectangular equation. So in your homework there's going to be a few of them. The first grouping of them are going to be lines, line segments, or rays. And then when you hit some further ones in your homework, I think 1 through 6 is going to be like what we've just been doing, and then 7 through 12 is going to involve, well, what we're going to see next. Okay, so we don't see, right there is a line, x equals -t, but y equals, there's a square there, so this is a parabola. So when you see one of these a parabola and one of them a line, our final shape that we're going to get is probably going to be a parabola. So let's see if we can do this. This is a little harder to actually say, oh, let's plot a lot of t points. We can say t, it looks like it starts at time 1. I'm going to try to find the parabola by solving for t in one of these equations, and I'll solve for t in the top equation. T equals -x. Then we're going to plug it right there. Now I'm only doing this because it's not a line, it's a parabola, so it's a little more mysterious. We have y equals -x minus 3 squared. Now if you actually FOILed that out, you would end up getting x squared plus 6x plus 9, which is the same as x plus 3 squared. So that's kind of where you're like, where did the negative go? You can factor it out of those two terms within the parentheses and then write it as -1 squared times x plus 3 squared, and you end up getting that way as well. So what is this? This right here is a parabola. The mother graph is x squared, and so this one gets shifted 3 to the left. Let's go ahead and graph that. Now I'm going to be actually a little more careful on this one, and I'm going to go ahead and make some tick marks here. So 1, 2, 3, and let's see what we have here. 1, 2, 3, 4, 5. Okay. So this parabola gets shifted 3 to the left. I'm going to do this in pencil. So 3 to the left looks like this. We have this right here, and it's a regular parabola, so you know usually it has the point 1, 1. It's going to have -2 that, and then we have this guy right here, and it's going to have 2. You know, I'm going to go over 2 and up 4. 1, 2, 3, 4. It's going to put a point right here, and over 2 and up 4 over here. So this is, you know, and I can actually plot some points. And so the parabola, now I'm doing it in pencil for a reason, okay, because the pencil has an eraser, and I'm going to need that eraser. So there's the parabola, and maybe I shouldn't put those arrows there. Okay, so that's what this parabola looks like. The reason I did that is because t has to be greater than or equal to 1. So for one thing, we don't know which way the orientation is going, and you know, let me erase these so you don't think the orientation is both ways. It goes both ways, but it's going to go one way here. And so let's see, t equals 1. So even though I did this, I'm still going to do this to kind of help me with the orientation on this. So if t equals 1, I'm going to plug t equals 1 into x. This gives me a -1. I'm going to plug t equals 1 into this. It's going to give me a 1 minus 3, which is -2, -2. Quantity squared is 4. So I have the point -1, 4, which is this point right here. This is the point when t equals 1. Okay, let's see. It says t is greater than or equal to 1. Let's make t equal 2 and see what happens. When I put t equals 2, I get -2. So already I know which way it's going. This is -2 right here. -1, -3. But let's just put the other one in there. We have 2 minus 3 is -1. -1 squared is 1. -2. So look at this. This is t equals 2. So it looks as if my parabola is starting here at time 1 and it's going this way. So not only does it tell me the right direction of the parabola, but it gives me the orientation, and it gives me that orientation right there. And you know, I'm sure if we put 3 in there, we'd end up getting this point. So here's time 3, and maybe time 4 is there, and time 5, time 6. We'll get rid of this part here. Forgot to label my axes, x, y. And there is my final result for the picture. They asked me to graph these parametric equations. They also asked for a rectangular, the rectangular equations. And the rectangular equation, you could either keep the -x minus 3 squared or go x plus 3 squared. Any of these are acceptable, so I'll write that down. Y equals x plus 3 squared. Now something's wrong with that answer. X plus 3 squared is the full parabola. This we have to limit the domain, and to limit the domain we're going to have to say that x is what? Think about it. X is less than or equal to -1. And that gives me the answer to problem number 5. It's a parabola. So you'll get some of those in your homework as well. Let's go ahead and see if we can find number 6. Maybe you can do number 6 on your own. Look at number 6 has another squared on the t, so you know this is not going to be a line segment. The line segments and lines and rays are a lot easier than these ones. So maybe you can figure out, you know, on your own, pause the video and do this one. Draw the graph and give the rectangular equation. Okay, so what I'm going to do is I'm going to solve for t in one of these equations. I'm going to solve for t in the bottom one. I'm going to get t equals, I'm changing things around as well, y plus 1. And I'm going to plug that into the top equation. And this is going to give me x equals negative, and then we have y plus 1 squared. So now, what I'm going to do is I'm going to put the y plus 1 squared on the left-hand side, and we had just gone over conic sections. I'm going to put the negative where the x is. And so this right here is a parabola in standard form, and we don't have to find the focus or anything like that, but we do see that the vertex, got to be careful on this one. I mean, this is x minus h, and there is no h, so the vertex is going to be at 0, negative 1, and this parabola is going to open. You know, it's a y squared, so it's not going to be up or down. It's going to be opening left or right, and because of that negative, it's going to open to the left in the negative direction. So that's highly traumatic. Notice on this, we never had any limitations on t. We didn't say t was greater than or equal to 2 or whatever. This is going to probably end up being a full parabola. So let's go ahead and graph this parabola. We have that and that. Here's x, here's y. We have 0, negative 1, which is right here. So I'll just put a negative 1 there. And this parabola will open to the left. Now you could, if you want, put in other values. You know, you can see that if y is 0, negative x is going to be 1, and x is going to be negative 1. So I mean, you could go ahead and plot some other points, but you'll end up getting something that looks like this. And we don't want to put arrows on this, so we're going to go like this, and hopefully it's not that pointy there. It should be all nice and smooth. The other thing we want to do with this picture is put the orientation. So how do I do the orientation? Well, let's let t equal 0. If t is 0, then I get the point 0, negative 1. 0, negative 1. So I'm right here at t equals 0. Let's let t equal 1 and see where that puts this bug. Is he going to go down here, or is he going to go up there? So t equals 1, I get negative 1 squared, that's negative 1. And then this is going to be the important one. 1 minus 1, which is 0. So at t equals 1, the bug is right there. So the question is, which way is the bug going? The bug is going this way. And if you put t equals negative 1, you'd probably have that point right there. So the orientation on this is that way. We have the graph. Do we have the rectangular equation? Yes, we do. It's right there. Let me just box it, because we really don't need to put anything else. We don't have to limit the x, or, you know, you might say, oh, don't I have to put values of x's? No, because this has a y squared, so this covers the whole parabola. And that ends problem number 6. Problem number 7 and 8. So look what it says. It says, don't worry about these problems. Okay, so before I go on with that, some of you are going to shut off the video. Here's the parametric equations homework. There are 12 problems, and then the next page gives you the 12 answers. So that will be included in the PDF. Some of you are probably going to turn off the video now. Oh, by the way, this is a short video from Monday. And that's alright, I don't have any problem with that. I think we have enough stuff to be put on the test. There is a test coming up, and when I say Monday, you know, the Monday that this video is posted on, there's a test coming up on April 24th, and it will go up through parametric equations. So the next video lecture you'll get is me doing some review. Maybe I'll be doing some of the homework problems and just kind of going over some of this. So now back to this. This is for the extra motivated student, and these ones here are very difficult to draw pictures of. Okay, because you can't really solve for t. I mean, you can, but it's going to be a mess. The only reason I wanted to show you problems like this is to show you that there's some funny pictures that happen when you do this. There's one thing I forgot to tell you about this one here. Going back to this one. Problem number 6. Is that a function? And you probably answered that question, no, it's not a function. It doesn't pass the vertical line test. But guess what? In some sick way, it is a function. It's a function of time. Because at time 0, the bug's there. And the output is where the bug is. At time 1, the bug is there. So the input is time and the output is a point. So this is, in calculus, we like to take derivatives of functions. This is how we can trick non-functions into becoming functions, so then we can take the derivative of those and investigate slope and other applications. So even though it is not a function, like when you go f of x, this is, a function of x. It still is a function of time, and then which that tricks this into being some sort of function that we can do calculus on. Well, the same thing with this. So what I'm going to do is, we're not going to do a rectangular equation of this because it's really tough to do, but I am going to show you the graph of this. And I guess I should have had the graphs generated on one of the graphing programs, but let's go ahead and see. This is kind of what I saw when I did the graph, and it ended up going like this. It's not going to be perfect. So that is the graph, and it goes like this. And you can actually see that if t is 0, you end up getting 0, 0. So this is when t is 0. And when t is 1, you end up getting 0, and you end up getting 1 minus 2, which is -1, so this might be the point. Oh, wait a minute, 0. So that is, -1, 0, so -1, 0. So I just wanted to show you there are some funky things out there. This one right here, if you've taken a trig class, you know that sine squared plus cosine squared equals 1, so you can do some funky stuff with that. You end up getting, for this parametric curve here, you end up getting this right here. A nice circle, and it goes around that way. So even though, and it actually has a radius of 1, and some of you would go, oh, the unit circle, yeah, whatever. But it's a circle, the rectangular equation is x squared plus y squared equals 1. And we have something, the circle is not a function, but we could still do calculus on it and treat it as a function of time. And at any time, the little bug is somewhere on the circle, and for the whole time he just keeps going around and around and around, and that's what happens as time varies. Some of you don't know what those mean, and if you take a trigonometry class, you'll find out what those cosine, this stands for cosine and this stands for sine. So that completes 11.10, the hidden section, the section that is not in the printed book. Parametric equations. You guys have a good day.